All right, welcome everyone. So we've now derived rate laws, and the question is maybe once you have a rate law, what can you do with it? So once you have a rate law, you can construct now using some integral calculus, we can start looking at concentration time graphs. So we use the experimental data to construct the concentration time graphs, but now we can actually draw them, meaning if we want to get back to this idea, so looking at concentration versus time and knowing whatever the shape is of the reaction that we're looking at, we can do some predictions for the reactions, right? So if we have the rate law, we can use some integral calculus to assist us in doing some predictions, knowing how long reactions will last, knowing how much product or reactant is left in the beaker, etc., etc. All right, so our starting point is for the first order reaction. And if you consider a first order reaction of the form reactant giving product, you can write something that says rate is equal to the average rate. So you might recall that it is minus the change in reactant divided by the change in time is equal to K multiplied by the reactant concentration to the power 1. All right, so this is a reaction. Reactant gives product. Then we take K multiplied by the reactants and we put them to the power 1, right? That's how we write a rate law. And to what we then can do is we can use some integral calculus. So that's not necessarily something that's examinable, but for interest's sake, you can take these changes and you can make them infinitesimal. And we can say then, well, the reaction proceeds between 2 points, 0 and some time in the future. And the reactants go from some initial concentration and a reactant concentration in the future at this time in the future. And you integrate the situation between them, and eventually we end up at something called an integrated rate law. All right, so if you do calculus, then you could follow this, but if you do not do that, that's completely fine. Then all you need to be able to do is use this integrated rate law, which I provide here. So once you have it, now let's look at what it consists of. So this bottom part here is the initial concentration, initial concentration of the reactant. And the top concentration is the reactant concentration at some time, two words, some time t in the future. So meaning whatever this t is that we choose, so if that's 20 minutes, then that means that is the concentration of the reactant when it is 20 minutes. Okay. The initial concentration means that is the concentration that we start with. All right. And K is, of course, the rate constant that you know what it is. Cool. So other things, so initial concentration, that also means it is the concentration when T is 0. So you could have gotten that from the derivation. So it is when T is 0, that is the concentration of the reactant when it is then. All right. Some important features of this. So notice that you don't necessarily need to know what your starting reactant concentration is or the reactant species concentration at a specific time. You also perhaps just need to know what the ratio is. So you can perhaps know, you can ask the question, how long will it take for 50% of the reactant to be used up, then you know that the ratio is 0.5. So you can work with a ratio. You don't necessarily just need to know that this one or this one is that. You can work with the ratio. You just need the rate constant, and then you can determine the time. Okay. Other important features of it. So for K, for a first order reaction, notice what its units must be. So we've already seen that in an earlier video, but this thing on the left hand side is ln of something. So it means it is unitless. So that means here on the right hand side, what must the units of K be? T has units of time. So that means K's unit must be per time to cancel with the unit of time. Otherwise, the right-hand side won't be unitless. So that means it must be something like per second, for example. And this means that our first order reactions are independent of concentration. So, or meaning the rate is independent of concentration. So meaning no matter what the concentration is of your first order reaction, it will always happen at the same rate for a given reaction. So what if you have the decomposition of potatoes and that happens at according to a first order reaction, then that will happen at the same rate no matter how concentrated your potato solution is. It will happen at a given rate. You can make it very concentrated, make it very dilute. It will happen at the same rate. Other uh, reaction orders will depend on concentration. And the reason for this is very interesting. If you were to take e to the power on both sides, so if you take e to the power ln of concentration R T R naught equal to e to the power minus kt. Then on the left hand side you end up with concentration RT over concentration R naught is equal to e to the minus kt, and then we can solve for concentration RT, right? Which gives us then R naught e to the minus kt. And do you recognize what this function is here? It is the function of something that decays exponentially, because that's e to the power minus kt. So if you plot RT versus t, you get an exponential decay. And all first order reactions are exponential decay reactions, or any exponential decay is a first order. And that's why it's independent of concentration, because it's describing exponential decay type mechanics, or exponential decay type kinetics, because it has to be independent of concentration, because it can only be dependent on time. All right, so any type of reaction that is first order in nature will only depend on time. So meaning the inherent mechanism of the reaction, and not the concentration of the reactants that you put in, because it is exponential decay. All right, so that's just an interesting fact. It's something that you can now see from the integrated rate law, and that you can see if you look at the plotting of the graph of it. Right, so that is our first integrated rate law. We'll now look at the next, the subsequent, the zeroth and the second order rate laws. All right, thank you for watching. I'll see you in the next video.